Hello. In this problem, we are shown this loaded beam system, and we're asked to find the principal stresses and the maximum shear stress at point H here on top of the beam. We're told that all three sections are solid cylinders with a diameter of 1/2 of an inch. So what's happening here is this beam system is undergoing these different loads. And on the inside of this beam, there are going to be some internal reactions. So to find out what's going on at point H, we need to go ahead and take the cross section there and analyze the internal reaction forces that result from these loads. So I've gone ahead and I've drawn the cross section here. What I'm going to go ahead and do now is draw the free body diagram of the reaction forces that are resulting from these applied loads here. So there's going to be a reaction in the X direction. There'll be a reaction in the Y direction and a reaction in the Z direction. And there will be a moment about each of these axes as well. So this will be MX, MY, and MZ. So for the time being, all of these are just facing the general positive direction defined by this coordinate system here. So what we're going to go ahead and do now is map out all of the values for these loads in order to determine what these reaction forces are. So we'll go ahead and make a little table that defines the distance from this cross section where the load is being applied, the magnitude of the load, and the resulting moment as a result of the geometry. We'll do that going in each direction. Hope I left enough room. And we will go about our loads. So we'll start with load PX. So first of all, load PX only acts in this X direction. So for the force, we can automatically go ahead and say there's 100 pounds in the X and 0 in the other directions. For the radius, we see that it extends out A and B in the X direction and D in the upward Y direction. So we have 12 plus 6 is 18 inches in the X and D inches in the Y, 8 inches. 0 in the Z. Now calculating our moments, perpendicular axes with an applied load creates no moment, but we can go ahead and get one resulting from this 8 inches in the Y direction. So we have 100 times 8 will give us 800 pound-inches in the Z direction. So this is all resulting from this PX here. There's that load in the X direction and the resulting moment from it being up on this little post here. So now moving on to PY. PY is being applied here in the negative Y direction. So we can go ahead and say negative 175 pounds. And there's 0 for the Z and the X. It is out A in the X direction, that's 12 inches. 0 in the Y, and C in the Z direction, that's 10 inches. And the resulting moments from this are going to go ahead and be 175 times 12. That's 2,010. My head hit the thing. That's 2,010 pound-inches in the Z direction. And 175 times 10 inches is going to be negative 1750 pound-inches in the X direction. Let me see if I can make that a little more clear. Okay, so we'll go ahead and move on to our last one. We have our load being applied at Z, also up here on this pillar. It is 18 inches out in the X direction. Matter of fact, just the same as the one up there as the PX. So let's go ahead and do this. The load's only being applied in the Z direction. So we have PZ is equal to 125 pounds. That's negative 125 pounds. And 0 in the X and the Y direction. And the resulting moments from this are going to be in both the Y and the X direction. So we have 8 times 125. We have negative, I'm sorry, it's supposed to be over here, negative 1,000 pound-inches in the X direction. This is becoming a mess. I'm doing my best to make it clear. And in the Y direction, we have negative 125 times 18 inches, which is negative 2,250 pound-inches. And there is no moment resulting in the z direction. So I hope that you can see that. My apologies for not spreading it out, but here, nonetheless, here are values that are resulting from these forces. So now we need to see what these reactions are as a result of this. So we need to get a value for our x, our y, our z, mx, my, and mz. And whatever is going on inside of the beam needs to be counteracting these loads that are on the outside of the beam. So the reaction in the x, we see that there's 100 pounds in the positive direction. So based on this axis here, there's going to be 100 pounds going to counteract that. So there will be negative 100 pounds in relation to this. So this force is going to be acting in tension. I'll get to it when we actually start defining the stresses, but for now, just based on this diagram, that negative 100 pounds is going that way. Our reaction in the y is that py, negative 175, but it needs to counteract it. So our reaction in the y is going to be a positive 175 pounds. And our reaction in the z is just going to be positive 125 pounds. Our moment in the x needs to counteract what's going on here. So we have negative 1,750 pound-inches, negative 1,000 pound-inches. So we have 2,750 pound-inches. In the y direction, we have just this one value that we'll go ahead and flip the sign, 2,250 pound-inches. In the z direction, we have 800 and negative 2,100. That makes a negative 1,300, but we go ahead and we switch that around to positive 1,300 pound-inches. So now that we have all of our reactions resulting here, and again, all of these are based on the vectors that you see here. So this negative 100 pounds going that way, 175 ry going this way, positive. We're now going to go ahead and take a look at the resulting stresses from these internal reaction forces. So we'll start with Rx, which is in the longitudinal direction. I'm better with numbers than spelling, but that is basically the direction, the axis that is going perpendicular to the face of the cut. So our reaction in X, we're going to go ahead and pick a view where we can see that force. We will do Y going this way and X going this way. So our reaction in X is a negative 100 pounds. So based on this coordinate axis, you can see here, our X is going to be going this way in tension, as we said. So to calculate the stress that results from this, we just have sigma X is equal to Rx over A. It's axial stress. Our area is going to be equal to pi times 1.5 inches over 2 squared. 1.5 divided by 2 squared times pi is 1.77 inches squared. So our sigma X will be equal to 100 pounds, that's positive because it's acting in tension, divided by 1.77 inches squared, which gives us 56.49 pounds per square inch, PSI. All right, so we can go ahead and move on to our next force now. Actually, rather, I'm gonna go ahead and put that on a stress block. It'll make things easier later on when we're going ahead and doing it. So we have X, Y, and we have X, Z. And this tensile stress can be represented on these two blocks here. At the end, we'll take all of these stress blocks and we'll superimpose all of the stresses together. We'll take the maximum, the block that has the most amount of stresses, and we'll use that to calculate our principal stresses. So moving on to our next stress, we have the reaction in the Y direction. Let me see here. Our reaction in the Y direction, we are again going to go ahead and pick an angle so we can go ahead and see what's going on. We have X going in and Y going up, and our reaction in the Y will be along the face of it going positive because our reaction in Y is positive. and that will be ry. So this is creating transverse shear. By the way, our little section H is located there, and on this one it was also located on top. Section H. Okay, so our transverse shear, tau xz is equal to VQ over IT. So our shear is going to be acting in the XZ direction because our little differential H exists in the XZ direction. So it's sitting on the top of this, and that means if you look at the little square that it would be, it extends in the Z direction and the X direction, and it's essentially lying perpendicular to that Y axis. It doesn't have a differential in that direction, so it can't experience shear in that direction. But that actually helps simplify this as well, because this ends up being equal to 0 because there's no shear stress on the outermost subject, on the outermost fiber of the subject. So we can go ahead and move on to our stress that reaction in the Z direction. Once again, we're going to pick a coordinate system that helps us see where that Z force is going. So here's our reaction in Z. And again, H is right here in the center now. So our tau xz is again equal to VQ over IT. Okay, so let's go ahead and solve for all these different variables. We have Q is equal to y bar prime. Y bar prime is just equal to the distance from the neutral axis going to the center of the shape that you're looking at. So here's our neutral axis, and here's the center of the semicircle. That distance there is equal to our y bar prime, which is 4r over 3 pi. And that will be times a prime, which is 1/2 pi r squared. So we get 4 times 0.75 inches divided by 3 pi times 1/2 pi, 0.75 inches squared. I'll go ahead and denote inches. 4 times 0.75 divided by 3 divided by pi times pi over 2 times 0.75 squared gives me 0.28125 inches cubed. All right, our T is our thickness, which is just going to be equal to the diameter, that's 1.5 inches, and our inertia is going to be equal to pi over 4 r to the 4th. 0.75 inches raised to the 4th. 0.75 raised 4 times pi divided by 4 is 0.4417 inches to the 4th. All right, so we now have all our values. We have an RZ, we have our Q, T, I. We can go ahead and plug in. Our reaction in the Z is 125 pounds times 0.28125 inches cubed divided by 0.4417 inches to the 4th, which is also multiplied by our thickness, which is 1.5 inches. 125 times 0.28125 divided by 0.4417 divided by 1.5 gives me 53.06 pounds per square inch. So if we're putting that on the stress block, then we only need 1 because it's in this XZ direction. And positive shear is in the direction of positive axes for both. So we're going to be looking at a block like this, 5306 PSI. Okay, so that goes ahead and takes care of all of our forces. We're going to go ahead and look at our moments now. So Our moment about X is going to go ahead and create torsion because it's in that longitudinal direction. So if we're looking at the end view, where we have Y going this way and Z going this way, our MX is going to be applied in the counterclockwise direction, 2,750 pound-inches. So that torsional stress, again in the XZ, is going to be equal to T rho rather, over J. So when rho, I'm sorry, let me go ahead and define where H is as well. H is going to go ahead and be on top. So for rho, because we're on the outermost fiber, that's just going to be equal to the radius. Our J is going to be equal to 1/2 pi r to the 4th divided by 2. It's 1.57 inches to the 4th. Okay, so we can go ahead and now write tau xz is equal to 2,750 pound-inches times 0.75 inches divided by 1.57 inches to the 4th. All right, and that gives me a pretty big shear. Let me go ahead and check my numbers on that. 2,750 times 0.75 divided by J, which is, our J is 0.75 to the 4th times pi divided by 2. Well, that's an interesting, I didn't get that number. Oh, let me see. 0.75 raised 4 times pi divided by 2. Okay, well, there's our value for J, is 0.497. I must have messed up here. Okay. 2,750 times 0.75. That's only going to give me a bigger number, isn't it? Let me see. Divided by 0.497 inches to the 4th. Yeah. 4,149.90 psi. Okay. So same thing, we only need to look at one stress block for that. They will be going in the positive direction. Once again, it's 4,149.8 psi. All right, moving on to our next moment, the moment about the y-axis. That's going to go ahead and create bending. So let me make a little drawing here. We have Z and X. And so what that means is our differential H is going to be right here in the center. So this, again, is going to be really nice because when bending applies, there is no bending that happens along the neutral axis. So this bending stress is actually going to be equal to 0 because our differential is here on the neutral axis. So we only got one left, our bending about Z. Okay, X and Y. And this bending is, let me see here, positive 1300. So we're going to be looking this way since we are looking at this. If X is going to the left and Y is going down, then that means we're looking down the positive Z axis, which means that let me think about this. X is going to the left, Y is going down. We're looking down the positive Z. So we're actually going to be, if X is going inwards and Y is going down, then we're looking down the positive Z axis, and that means that this is the wrong way. We need to be going this way, counterclockwise. Okay. 1300 pound-inches. Yes, I'm convinced. All right. So, let me see here. Our stress that results from this, where our differential is going to go ahead and be, our differential is then going to be on the bottom because it's parallel to, or perpendicular rather, to that y-axis. So our stress that results from this is going to be in tension because the bending is pulling on this side outwards, and it's compressing on this opposite side. So we have our stress in the X is going to be equal to my over I, which is equal to 1,300 pound-inches times 0.75 inches divided by our I value, which we got up here is 0.4417 inches to the fourth. And that was because pi over 4 times 0.754. Well, that's disappointing. I'm now getting a different value for I, which correlates with the one that I have on my other paper. So I need to make this correction later, but I'll come back for that. So our I value is actually 0.249 inches to the fourth. I thought that there was something wrong there. 1300 times 0.75 divided by 0.249 inches to the fourth. So that gives me a sigma x equal to 3915.66 psi. Okay, so going up here and just correcting this, my I value is equal to 0.249 inches to the fourth. And that means that when I'm coming through and calculating here, that is 0.249 inches to the fourth, 125 times 0.28125 inches cubed, divided by 0.249 inches to the fourth, divided by 1.5, gives me 94.13 psi. 94.13 psi. All right, that looks better. Okay, so we now have all of our stresses, and I can go ahead and put this on the stress block as well. We have going on in that direction, and we also have Z and X in this direction. That's 3,915.66 psi in tension. So now we need to go ahead and superimpose these two stress, all of our sets of stress blocks together. So I think I've got them all included there. So now if we draw all of our stress blocks, we have, let's see here. I'm botching it. We have X, Y, X, Z, and Z, Y. Okay. Actually, I'll go ahead and do it. Y, Z. Yeah, because we have our Y going upwards. Okay, it's not going to matter. We don't need it anyway, because all our maximum stresses are not going to be on that block. I can tell right away. So from this block, we have 56.49 psi acting in X, acting in tension. Otherwise, we have this tensile force that results from bending, which is 3,915.66 psi. So that gives us a total of 3,972.15 psi acting in tension. So that's going to be our sigma x. Let's go ahead and look at what we have left over. We have our shear stresses. We have 94.13 coming from 94.13 psi coming from our reaction in Z, and we have 4,149.8 psi coming from our torsion, and that'll give us a total of 4,243.93 psi acting in tension, or I'm sorry, acting in shear. So we now need to go about finding our principal stresses. So we've taken all of the stresses that result from the applied loads and we've superimposed them together onto the same blocks, and we're now going to go ahead and find the principal stresses that result from this block, because this block has the most tension, the most stresses acting on it. All right, so sigma 1 and sigma 2 are equal to sigma x plus sigma z divided by 2 plus or minus the square root of the difference between sigma x and sigma z divided by 2 squared plus the tension, the shear strength, the shear stress squared. So we have 3,932.15 psi plus 0 psi divided by 2 plus or minus the square root of 3,932.15 psi divided by 2 squared plus 4,243.93 psi squared. All right, so 3932.15 divided by 2, we have 9,666.08 psi plus or minus 3932.15 over 2 squared 4243.93 squared 1, whoops, we have 1 plus the other, take the square root, we receive 4,677.22 psi. So adding those up, we have 1,966.8 plus 4,677.22 gives us a sigma 1 equal to 6,643.3 psi. Our sigma 2 will be equal to 1,966.08 minus 4,677.22 psi, which is negative 2,711.14 psi. And our maximum shear stress will be equal to this value here, 4,677.22 psi.